All right. Some of this I'm going to have to just have you go back if you really want to make a detailed drawing of this. It'll be on the YouTube videos. But I just want to speak about a couple of these images, specifically the math inside the processor. The way things work, every time you perform an operation like the add instruction, a couple of things are going on here. First off, the ALU is told to add things together. Furthermore, it's told what two registers to operand on. There's a source, control. These are multiplexers, right? So we choose which of the 32 registers we're going to. Those get sent to the ALU. The resulting 8 bits is sent back, and there's a destination, all right? And that chooses what destination register it's going to go to. One other thing I want you to keep in mind that's happening here is the ALU is determining if the math was done correctly and if certain interesting events occurred. And it's being written into that status register, one with all the letters. So just be aware that that's a thing that is happening. We've done that. We've done that. I want to go over a couple. I want to go over solutions. Solutions to the add 19 to 95 problem. My solution looks a little something like, first off, everybody's turned it in, right? Scout's honor? Okay. Here's my solution. LDI are 19, 19, LDI are 20, 95, add R19, R20. That's it. That's the whole thing. Now, secondary question, follow-on question. 19 plus 95 is what, 114? What register has 114 in it? 19. R19, because data flows, if you're dyslexic, it flows from left to right, but normally it flows from right to left. Okay. Second one, I've got it already set up here. 19 plus 95 plus 5. First solution. Let's go to the phones. Yeah, here's one. Right, you want to do my job? I'm kidding. I'm not mad at him, by the way. For those of you who have no clue who I am, like, I would not make fun of him if I didn't know. LDI. R. 19. 19. LDI. R20. 95. So far, same as last time. And we just have one more number, so let's load that right up. 21. 5. Okay, and then we can keep going. Add R19 to R20. And as we figured out, that gives you 114 in register 19. So then I can add R19 again. My handwriting is getting worse as the day goes on. R21. That's a solution. A solution. It works. It does give you 119 in register 19. Now, you could have used any register you felt like as long as it was greater than 16. If you used our register 0 to 15, that breaks the rules of LDI. So that's a thing. It's not... go ahead. I totally did. I totally did. Hold on, I can go back. This is the advantage of having all my stuff. First, LDI. Double click. Right there. Okay, continuing on. Where was I? Here. And here. Okay, second solution, which in my opinion is the better solution. Because here's the problem. Let's say I expanded this. Plus 50, plus 75. You know, I kept going. All right. When does it become a problem with this type of solution? Yeah. When you run out of registers. And because LDI is a limited subset of registers, you run out of it with like 16 numbers, that's rough. So the second solution, which I know a few people I saw do, is to start reusing registers. LDI R19, comma 19, LDI R20, comma 95, add R19, comma R20. Then overwrite R20. We've used it. We don't need it anymore. R20, load with 5, add R19, comma R20. Same instruction, by the way, but R20's value has changed. This is better. This is a better solution. It's R20. Oh, sorry. R20. Okay. Okay. So jump back from individual, because we've got 130 that we'll eventually get through. Let's step back from that for a second. Let's start classifying the types of instructions you can have. And we'll start with 2-register mode. 2-register mode is anything that takes 2 registers. Okay. I'm going to give you a new one. Subtract. It's the opposite of add. It does exactly the same thing, and ooh, that's an error. It shouldn't be R1. It should be R0 to R31. Right? It's exactly the same as add. RD, R, or RS. It does the same thing. Instead of RD equals RD plus RS, it's RD equals RD minus RS. It's called 2-register mode, 2-register addressing mode. Anything that takes 2 registers falls under this category. While we're sitting here, grab this. Somebody find me another thing that looks like it might belong to this category of instructions. Just scroll through. Tell me what the operand is or the mnemonic, and tell me what it does. Logical AND is one, yeah. AND takes RD and RR, and what does it do? It bitwise ANDs each bit of the operands together and stores it back into RD. And it does store it into RD because, once again, data flows from right to left in all these instructions. There's quite a few on the front page alone. Actually, most of them are on the front page. Okay. So that's 2-register addressing mode. While we're thinking of it, the other instruction we knew about was 1-register mode, but it's a specific kind of 1-register. It's 1 register with an immediate instruction. Let me see if I can find another one. SBCI, it's like 5th down there. SBCI is also a 1-register addressing mode with immediate. I know that it's an immediate because it says K. K is kind of a dead giveaway that it's some kind of an immediate mode if it's working with a register. So one might ask, what is a 1-register addressing mode without immediate? I'm so glad you asked. Single register addressing mode is where the other operand is kind of implied. And the 2 instructions I want to call to your attention right now, increment and decrement. Anybody who's come from a C background is familiar with the plus plus and the minus minus operator. And that's what this does. But it does it on a single register. And again, RD can be anything R0 to 31. There's no limitation. So, all right, let's start looking through this. Somebody find something else that looks like it is a single register addressing mode, no immediate part. There's a few on the first page, actually. Oh, they're kind of pseudo instructions, though. What? One's complement. Yeah, it takes 1 instruction. That actually is a valid one. Yeah, COM, C-O-M. And also neg. 2's complement. Yeah, 1's complement and 2's complement. Well, mostly. There are a few that are kind of fakes. Look at clear. clear register, CLR. If you go over to the opcode, it actually doesn't have an opcode. It's actually a cheat. It uses exclusive OR with itself. So it's not a real instruction, but it kind of pretends to be. So mostly, yeah, just anything with RD in it. That's it. So if you see an RD and a K, that's probably some form of immediate mode. If you see just an RD, that's a single register addressing mode. Okay. All right. So far, we've basically just lived here. We've only lived in here, inside the CPU. We've got the general purpose registers, and that's it. Well, there's so much more to the world than the general purpose registers. Let's talk about this guy, because this is the next place we're going to go. It would be nice if we could put data in storage and come back to it later. So we only have 32 registers. That's not a lot of numbers. If we need to operate on thousands of numbers, we're going to need to access RAM. Okay, so while we are sitting here, I do want to point out that all of these individual boxes, okay, fall into something called memory mapped I/O. All the peripherals, this is a thing you need to know, all peripherals share the same virtual memory space. Virtual memory space is this big tall box that I keep drawing with a zillion locations in it. Memory space is just a list of contiguous memory addresses going from 0 through to FF, okay, or whatever the data size is. So all the peripherals share this same virtual memory space. It's memory mapped I/O. So the RAM is shared in the same space as the general purpose registers, which is shared in the same space as everything else. Oh, I didn't want to do that. As a rule, this is what we've got going on. We've got 3 sections of memory. At address 0, we have the general purpose registers, R0 through R31. They're part of the memory space. You can access those as memory. So by the way, 31 is 1 F hex. Starting at 20 hex, we have another type of memory. It's the I/O registers. I colorized these things here. So the general purpose registers are yellow. The I/O ports are red. The RAM is green. So if I go over here, I/O ports are red. RAM is green. And I put a note here. Hold on to this red thing for a second. Just don't ask me about it yet, please. That goes up from 20 to FF. And then there's RAM. This is the real physical memory. Starts at 100. It goes up, depends on what chip you've got, how big it is. Ours, I think, tops out at 3FF. Okay. And then everything else is kind of, well, anybody else, it's reserved for future use. But that's our memory space. So there's 2 questions. We know how to access the general purpose registers. We can LDI all day long. We can load immediate all day long. But for this, there's 2 questions I have. How do we get data from it? And how do we put data into it? Those are my 2 questions that I want to ask. And again, we'll get to the red section in a second. Well, to deal with this, there's another instruction. So we're going to go to a new instruction now. That instruction is LDS. Load from data space. And this is slightly different. This K is a K16. And we also have the complement of load is store. So we have load from data space, store to data space. And both of these are K16s. And here's the first instance where you actually see that the direction of data travel is maintained. So data always goes from right to left. So here, we're going from a memory address to a register. Here we're going, when we store, we're going from the data in a register, we're putting it into memory. So things you need to know, LDS, RD, K16. K can be anything from 0 to FFFF. RD can be anything from 0 to 31. STS, now it's the order of the operands is flipped. Now it's K and then R. We use RD to indicate destination, RS to indicate our source. but that's more of a loose convention than a hard and fast rule. Oftentimes you'll see in the literature capital K is an address, lowercase k is an immediate. I try to be a little bit more specific. K16, 16 bits of immediate mode information. And that's what we are giving here. We're giving it 16 bits of data. That corresponds to the address in memory you want to access. All right. We're going to do, hold on, everybody turn your head and cough here. Erase. Oh, that's a little too big. Go one step smaller. Go one step smaller. There we go. Okay. So I've got some code here. And the goal is to analyze this code. We're going to be using this new instruction now, LDS and STS. So what I've got over here is I've got the start of stepping through this program. I'm going to run through it one step at a time, one line at a time, and I'm going to write down what is in every location at every step. So before we start this, I'm going to say that I have no idea what is in R0, no idea what is in R1, and I know that there's some data in 300. Rather than using a number, I'm just going to use a variable. For now, I'm going to say that at address 300, alpha, and at 302, beta. That's all of the locations that I'm going to be using in this program. R0, R1, 300, 302. That's it. So what's the result? And where is it? Well, after I execute this LDS instruction, here's what's going to happen. I'm going to take whatever is in address 300 and I'm going to store it in R0. So that means I'm going to overwrite I don't know. I'm going to overwrite question mark with alpha. Then I'm going to do another LDS. And okay, so that's going to put beta in R1. Everybody good with the basic concept here? Take from whatever is in memory location 300, you put it into a register. Now, adding R0 to R1, well, where is it going to end up? It's going to end up in R0. So I'm just going to say, all right, alpha plus beta, whatever that number is going to end up there. Ooh, I got ahead of myself. What is in address 300 after I've loaded from 300? Yeah, it stays the same. It's still there. And beta hasn't been touched at this point. After I load from... Oh, hold on. Whoa. Slow your roll there, Dr. Vile. Let's try that again. All right, so we've loaded up. Oh, goodness. I've flubbed everything, guys. Okay, let's try this again. Okay, so first we load up alpha, then we load up beta, then we add alpha and beta together. Sorry, I was going a little fast there. Now, meanwhile, all this other stuff, even though we've been copying from it, hasn't changed. So when we do the add, R1 stays the same, memory is still the same. Okay, now, once we do the store, this is where things get interesting. R0, whatever the value of R0 is going to end up in address 302. So we're going to overwrite beta. So whatever alpha plus beta is going to go there. A still has whatever alpha plus beta is. Beta, alpha. And we're done. That's analyzing this code. So LDS and STS, you just give the address, whatever address you want. It can be anything from 0 to FFFF. All right. Now, we've taken care of this green section. So, we know how to access this. Okay, great. We know how to access this. Okay, great. Now, the I/O registers, they deserve a little bit of an introduction here. They control the physical pins. When we were talking about all those pins, PB0 through PB7 and so forth, this red block, this section of memory, is what actually physically controls them. And they're so special, And they're so time sensitive that there are special instructions just to talk to this block of memory. All right. So whereas we had LDS and STS to talk to the green section, talk to RAM, now we have two new instructions. We have in and out. It is convenient that to access the I/O registers, you have in and out. In, out, I/O, okay, input, output. They follow the same basic setup. We have a register and an address, but this is A. This is different from K because A is what's called an I/O address. It's an address of something in the I/O section. So in is analogous to LDS. Out is analogous to STS. Okay, so if you're getting something in, it's going to a register. If you're putting something out, it's coming from a register. And that is why the operands are arranged as they are, because data always flows from right to left. And this is where those special purpose or special function registers come in. That red section is nothing but special purpose registers. And while I'm thinking about it, pass these out. Grab a couple here. Send that. That's just one page. Just one page. Pass those around. That is a list of all of the I/O registers in the processor we're going to be using. Okay? You don't have to know what they all do right now. Okay? But on the left side is the name of the register. On the right side is what the little pieces inside of those registers do. But they're special purpose. They're not just for holding a number. Setting particular bits in specific combinations does stuff. And we'll get into that stuff. So the I/O registers are actually split into two sections. There's the special purpose registers. That's the beginning of it. The first 32 or 64 of them? 4 times 16, 16. Yeah, the first 64 locations are the basic I/O registers. Everything after that is what's called extended I/O. You have the whole thing, I/O and extended I/O. You can see the full names of all this stuff in the data sheet, but things that might be of interest to you: the control for port B, the control for port C. I seem to have missed the control for port D, but that's in there. Timers, EEPROM, SPI, interrupts, the stack pointer. Stack pointer is super important. Its list, I gave them all away. The stack pointer is what, 3F or 5F, depending on which column you look at. Am I right? SPH and SPL should be at the top. It's there, I promise. Well, so we need fast access to this stuff, this basic stuff here. And so we use in and out. For the extended I/O section, we continue to use STS and LDS. So the first problem you're going to encounter as you begin coding larger things is, which assembly instruction do I use? Do I use in and out? Do I use STS, LDS? Well, actually I have a copy in my back here, I think. Yeah. So if you look on the left-hand side, on the first page, the leftmost column has two sets of numbers here. Those two sets of numbers, let me do that just so you can actually see what I'm talking about. Okay, it has two sets of numbers. Those two sets of numbers, one corresponds to the absolute address. If you're going to use LDS or STS, you might use that address. The ones not in parentheses, there we go, I can actually see it, so you'll be able to see it. The ones not in parentheses, like 1F in next to 3F there, that's the I/O address. So when you use in and out, there's actually a special procedure. You actually subtract 20 hex from what you're dealing with. Now, in practice, you don't need to worry about this. But what we're going to do a little skills exercise. I'm not going to collect this one, but you've learned a few new instructions. You've learned LDS, you've learned STS, you've learned in, you've learned out. Write a program that adds the contents of the pin C IO register, so you're going to need this piece of paper, to the contents of the pin D special function register, stores the result in location 90 of RAM. So this is putting everything together that we've talked about. So first off, before we get into the formal thing here, can somebody find pin C and tell me what its address is? That's an excellent question. Why don't you give me both?
Pin C is X06 and X26.
26. Now, which one of these is the IO address and which one of them is the absolute address?
26 is the I.
False. Okay, the IO address is 6.
But I have it wrong, so the absolute address is the one in parentheses?
The absolute is in parentheses. If you actually look, all of the rest of them have parentheses. So only the first part is IO. So this is absolute. So what about, what's the other one? Pin D. Where's pin D? 09 and 29. Yeah, they always differ by 20, by the way. It's always a difference of 20. So the IO address is 9. The absolute address, 29. Yep. Yeah. Oh, you can't see any of what I'm writing. Well, thank you. Boom. Much better. Okay. So write a program that adds the contents of the pin CIO register to the contents of the pin D special function register. Store the result in location 90. That's just regular RAM 90. Nothing special about it. So this is going to require almost all of the things you have used except for one instruction. Take a couple of minutes. Do you want this to count as your attendance this hour? Actually, yeah, this is a great thing to count as attendance. So if you're doing this on a sheet of loose leaf, grab a sheet of paper from the printer. Because there's about 7 ways we can do this, and I think it might be worth it to go through several of them at least. Oh, let's pause it here so we can